in that sense that can be useful later on. Then second point, disclaimer is because of the date, so I make a mistake in the slide, so apologize. It's not 5th, it's 6th, but anyhow, hopefully you can allow me the short mistake. Just starting, first of all, is the acknowledgement. So I need to thank the Spanish Agency for Research. And then because the funding provided to the project digitalization as key enabler for asset management digest is because that kind of seminars take place. So thanks to the Spanish Agency for Research. Then next point is to present to introduce the focus of what we want to cover today. The idea is to move into the general overview of what machine learning is, generally speaking, and the key points for machine learning itself. Then distinguishing from other stuff like deep learning, generative AI, etc. Then going to the same discussion on deep learning, when and why. And then to close that because it's the biggest part of the amount of effort we normally spend, we will make some wrap-up consideration, and then covering transfer learning and reinforced learning, because potentially some of you are related to that kind of techniques as well. So limitations are basically we have limited in time. Then we expect that you are, let's say, familiar with programming techniques and tools, etc. So feel free for sure to at any time to drop your comments or questions through the chat. Then I will try to manage at the end. But yeah, feel free to ask for any kind of comment you want to make. And then just the last disclaimer is for myself. So I wanted to introduce myself, who is speaking. Yeah, so basically myself, I'm located in what should, let me call that industrial management, but with a strong connection with digital technologies. So basically the intersection will be this one or this other one as a center of the topic. Then next is to just start with the general overview. Probably you're familiar with that kind of representation, showing all the techniques according to the main title, like artificial intelligence involving everything, machine learning involving many of the things, and then neural networks, deep learning, and generative AI. Although people represent this and suppose that every single circle involves all the other inside, for practical reasons, when we talk about machine learning, we will talk about specifically not tools related to deep learning or to generative AI. And the same for the deep learning. We will not cover specific topics related to the inner circle, just to make the clear distinction, because sometimes it makes people confused, let's say. Then imagine we need to solve a problem using machine learning techniques. And then the first question, so we face the problem that, okay, I need to create a model explaining the behavior of this or that. And then how should I start working? First recommendation is to use a methodology, helping you to not make big mistakes. It's for sure it's not foolproof, but it provides a guidance which is always valuable. The point is, which methodology should I use to implement and to develop my approach? Then I can recommend you ChrisDM, which is a stepwise methodology coming from the, let's say, beginning of the century. So from 1999. And then, yeah, so basically make the structure based on steps like, okay, first of all, we need to understand the business needs, then the data we got to explaining the behavior we want to model to estimate, then data preparation, then modeling, assessment, and then deployment. Be aware that also modeling is here, and most of people are attracted, I mean, myself as well, attracted to these techniques. Actually, this is potentially the less relevant part of the game. I know it's something which is shocking, but it's the truth, at least in terms of effort. In terms of effort, the biggest part is probably data preparation in connection with data understanding. So they both are the biggest time-consuming steps, without dismissing the business understanding itself, which is also very relevant. And then another critical point out of modeling is the evaluation. Evaluation normally is hardest because you are willing to convince people that your model is fantastic and it outperforms whatever other strategy out there. Sometimes it's true, and sometimes it's not so clear. And then it is, let's say, sometimes sad because when the things are not as expected, you need to jump back until the business understanding, because we probably make a mistake in understanding how, in which way we need to do and to develop this or that, and then we need to repeat several steps. Sometimes it's business understanding, sometimes it's data understanding, but still it's kind of, oops, it doesn't work as expected. And then last but not least, deployment, which is not just release the models. We are on this assumption that we are not preparing just a paper for a publication, because in that case you can put whatever, and it's normally more journals are much more concerned with replicability, but still it's an open question. So yeah, so it's a matter of lying, but still assessment is something which is not so hard. When you need to deploy in the real life those models, and then they need to live daily working, so the deployment is something very relevant. And then indeed, it's not just only to drop off the models themselves, but it involves also dissemination, it involves also training of people, it involves many different things that requires attention from an effort, let's say. Then what if you don't like CrisDM because it's too old? And okay, there are some others. I can recommend you, for instance, Teams for Data Science Process, for instance, which is the last one, well known, let's say, but there are many others. So if you see here, the team of data science process is basically close related to CrisDM. There are things which are not there, for instance, more detailing in model assessment itself, not the assessment, the whole pipeline, but just the model. And also pipelining in terms of deployment and exploration, which is much more, and also customer acceptance, which is critical for sure. And then also something related to data spaces and repositories, etc., which was not explicitly identified in the field of the CrisDM. But anyhow, my strong recommendation is pay attention to the methodology, because it will help you. Of course, each of those blocks have steps inside, and then don't forget to follow them. Then, sorry. Yeah, so as I told you before, to me, the biggest critical step is preprocessing. Keep in mind that those models run under the hypothesis that there is no physics or other knowledge coming into the model. Only they need to learn what they see, what they understand from the data we provide with. Then if we put some data which are not reflecting what we want to describe, the model will learn from that and nothing else. So then bias between your expectation and the outcome of the model will be for sure a guarantee. Then problems, because normally when we learn from real data are in some cases not well structured, inconsistent, with errors coming from measuring systems, sensors, from different type of errors that we got them inside of the as a fuel for the model to learn. So the model will learn from those errors as well. And then, indeed, depending on the type of the data, it's not the same to have structured data and to have non-structured data. This is completely different game. So from now on, we will assume structured data as for the first part of the presentation at least. Then, yeah, so that is a good comment, but what tasks specifically are in here? What I need to do? So you need to pay attention at least to those 4 main topics: data cleaning, data transformation, potentially, if you are doing unsupervised learning, data reduction, and then structural operations probably as well you need to care of them, in that step. So data cleaning is self-explanatory. So you will get data from the real life which is not complete. So some sensor fail in measuring, then they provide no data. Some records are partially completed, etc. In other cases, you need to deal with outliers. So samples where one sensor measures dramatically wrong. So it is out of scale, and then it provides a number which is not physically possible. Then but it provides that number. So then it's up to us to handle them. We need to be very careful about the duplication, to remove repeated samples or very, very close samples, because they can keep in mind that if part of them goes to the training and part of them goes to the test, you will measure the quality of your model based on information which was already there for training, so it's already known, and then it is not fair, let's say. Then data transformation, like normalizing data, providing standardization, scaling, etc. Or indeed, even more important, if you are dealing with classification, categorical encoding. So if you got data which the range goes between 1, 2, 3, 4, and 5, imagine, and then normally machine learning techniques used to see that kind of range like an integer or a numeric description. Things is not so hard when distance between those categories 1 and 2 and 4 and 5 are similar. But if it is not, then it is a strong bias introduced in the model, just not telling the model that, okay, keep in mind that this feature, that variable, is a categorical one. Then 1 and 2 are 2 different things, not distance 1 unit from the one from the other, or 4 and 5, or 2 and 3. So be aware that these are completely different, and the distance between 1 and 2 is 1 or 10 kilometers. It's not just 1 unit, right? Then, yeah, so then that kind of things need to be carefully handled, because again, if you introduce wrong or bad quality information, the quality of the model you can expect it will be extremely good. Okay, just before moving forward, I wanted to ask you to visit booclub.com and to introduce the code YAPQQO. Then I need from you to know some answer to specific query, to at least for me to know where you are and what is the existing knowledge behind. So please feel free to navigate to and don't close it, because there are some other questions along the presentation. So it's multi-answer. So There is one answer. Okay, probably I make some, not sure if someone else, okay, you are coming. So I biased I show you the answer before getting a good a number of them. Yeah, okay. Okay, okay. Any other answer, please? Because we are 8 people. Don't be concerned on how people are answering. Make your own choice. And remember, machine learning means only machine learning. It's not deep learning. It's not generative AI. It's nothing else like just machine learning. Statistical tools to be used mainly with supervised learning, although this is possible to do something with unsupervised as well. Okay, for answers. So we need to move forward. Well, I disagree on some of your. I know. When you say optimization, I can imagine you are thinking in that minimizing the errors. Yes, but this is not exactly optimization. It's a technique to solve one problem, but optimization is another thing, like another techniques like genetic algorithms and other stuff. And then the answer for me will be those. Oops, sorry, I'm not sure what happened here. Yes. So, oops, there is a mistake before. So, yeah, regression is true, classification is true, clustering is true for sure, and then association rules, which you didn't realize, is also true. So, if you are in the business of the retailing, then association rules you will be very familiar. If not, potentially you didn't face that kind of technologies. Okay, thank you very much for the participation. Another one, just for me to close the picture. What kind of techniques do you see as relevant for machine learning? Any other answer, please? Yes, thank you. May I motivate any other participant to say something? Okay. Well, I need to say that I'm a little bit surprised somehow. Now, okay, decision tree comes from the previous, so that will be expected for sure. Then I will expect more let's say support for the linear models, actually. But okay, so for sure not CNN. I know CNN is not the news channel for sure. And the convolutional neural network is a deep learning technique. It's not a machine learning. and LSTM is the same. And genetic algorithms is for optimization, it's not for machine learning itself as such. Okay, thank you very much. I see where we are more or less. Okay, then when to use machine learning recommendations. Okay, if your problem falls in something which is regression or classification or clustering or association rules, then this is the real place for you to grow the model. Indeed, if you have not a massive amount of samples, which is unfortunately the reality in many applications, because you rely on, I don't know, medical tests or mechanical tests for materials, etc. Then you don't have a very large amount of, meaning that we are talking about tens of thousands of samples, right? Then if your data fits like an Excel sheet or SQL table or CSV file, then like rows for samples and then columns for variables and features, then this is also a classical approach for that kind of techniques. Or if you need to explain decision made based on those features, on those attributes, like in healthcare, credit scoring, or many other, then association rules can help a lot, or trees as well can help a lot. And then if you don't have, although you have many samples, etc., you don't want to spend big amount of effort and budget using expensive hardware. Keep in mind that deep learning techniques and generative AI techniques are very expensive. And then they require to be careful with them. So depending on the situation, so depending on your context, for sure. But then this will be basically the main tips for doing generative machine learning. Sorry. Then I assume that you know Python. You use kind of graphical user interface like Visual Code or Jupyter or Data Wrangler or PyCharm or any other of those. And then probably if you are using Python and you are trying to do machine learning techniques, then you are familiar with things like NumPy package, I mean, Python package like NumPy, Pandas, Polars, etc. So these are basic tools for working with arrays, matrices, vectors, etc. that you need to use to implement your training pipelines, etc. Indeed, if you use, let's say, that kind of you already use machine learning, if not, be aware that there are already prepared and ready to be used very, very good packages like Stick-Learn, helping you to do classification, regression, clustering, data preprocessing, lot of things. Indeed, some other specific packages like Extreme Gradient Boost or Light Gradient Boost Modeling or Cat Boost, some others helping you to deal better with the non-classical trees, decision trees, that they are very convenient and very well suited for dealing with them. Then I believe these are things we need to be aware of. I want to show you, let's see if I'm able to, just an example of, well, this is a visual code system for a product from my side, let's say, allowing to make prediction for energy consumption of products being produced in a steelmaking plant, right? Then I wanted to show you that kind of packages in here, like for linear model, the metrics, preprocessing, ensembling, you see all of them here. Then I also use the time to encourage you to do effort in documenting, let's say, the code you produce. If you are dealing just with research and your own research, that's fine. If you are aware of that my code need to be maintained and supported by, and used by others later, try to make documentation in a structured way, like docstrings or similar stuff, because that will help a lot to you in the future and other people for sure. Well, that means try to be object-oriented as much as possible, and then try to make for any method you produce inside the class or outside the classes, try to produce documentation of what the class is expected to do and what the methods are expected to do as well, right? So don't spend and don't be ashamed to do it. Like here, for instance, documentation for the class, which is the name is self-explanatory, but okay, anyhow. And then also for the methods inside, making clear what is expected and what is done by the tool. And try to be, let's say, and this is a tip as well, try to be not very declarative and try to imagine that things happen and errors could be there and they can destroy. Then try to manage to catch, let's say, potential signal error, and then try to manage the exceptions, trying at least to inform people what's going on. If you do the things well, you can produce automatic documentation like this. This is made by Sphinx, and then it helps you a lot in showing the architecture of classes you produce and how to maintain, how to use. Then this is automatically done by the documentation you put in the code you created. Indeed, you can include some, let's say, class diagrams or sequence diagrams or any kind of stuff you believe it will be helpful for your people when they need to use or they need to maintain or whatever the tools you are using and creating. And be aware, because the more and more, even for science, as I told you before, many journals start to ask for replicability, and then they ask reviewers to check, okay, is the result supported by the, or are the results supported by the material provided, is trustable, and then that kind of things is a good practice that you can use for your research as well. Okay, then that's all the tips for machine learning. If you have a specific question, feel free to raise them. Then next question is, what is for deep learning? What tools are for deep learning? According to you? Okay, this field is much more known, I see. Yeah, so basically, the two people who answer only make a small omission, but they are right. So anything else to show the knowledge? Yes, exactly. Yeah, basically, yes, exactly. So this was the right answer. Thank you. Yes, perfect. Yes, so when to use deep learning? Well, deep learning is kind of a subclass of machine learning in the concept that, okay, it is able to do regression as well, classification as well, clustering as well, but when things are slightly different, meaning that, okay, for sure you can reapply in the same way like machine learning, but this is much more convenient techniques for when the features are not so evident. For instance, images or audio or video. Then in those cases, feature identification is not direct. It's not a column in the Excel file, right? In those cases, deep learning can play a good job, because deep learning involves inside their own technology the feature identification or the feature engineering, as people used to say. Then this is very helpful for us in those cases if we are facing that kind of problems. Costs. There is no free lunch, as the US people say normally. So the cost is that we need normally much bigger amount of samples to play the game. Then, yeah, so my recommendation is the step, if you are dealing with video, with audio, with images, etc., then you are forced, and you don't want to do your feature engineering yourself. In that case, there is no way to go into deep learning. Otherwise, the best approach is to start with simple models, and then try to see the evolution, and then when I need to go forward. Normally, deep learning does very well, performs very good when dealing with complex and nonlinear relationships, which are hard to handle in other cases. For instance, nonlinear models are not able, so linear models are not able, or rich, or whatever. And then discretization is sometimes heavy, especially in high dimension spaces. So yeah, in that case, could be relevant. When to decide to use deep learning or generative AI? Well, there is a very easy way of answering. Deep learning is when you need to analyze, categorize, or predict based on existing data. And generative AI is when you need to create new content, new things, answer to questions, that kind of things is the way for a generative AI fail natively. And then for deep learning is, although there are overlapping for sure, because adversarial generative adversarial network, for instance, is in the middle of the game. But anyhow, it's a clear difference. Then tooling for deep learning. Well-known tools are PyTorch, which is probably the most known framework to grow model and to declare and build up models. TensorFlow Keras is also a good alternative to PyTorch, depending on is lighter and more convenient in some cases. It's a matter of you as a researcher to decide what to implement and what to do. And don't forget Paddle, which is a tool coming from Baidu, from the Chinese developers, that they are extremely good performance and very good in dealing with distributed edge devices. So these are let's say in the tool books, the things we need to find in there should be that. And then for visualization, which is very important, I didn't mention it, but when you are dealing with data understanding and data preparation, normally I will make the tip later, but it is extremely important to realize and to feel how the data behaves. Then there are well-known packages, well-known tools inside Python in that particular case, or other language tools like Julia or others, Matplotlib or Seaborn, well-known packages for static plots, Plotly for dynamic and responsiveness graphs and plots. And then if we are dealing with massive data, in that particular case, those techniques will not work because they can handle hundreds of millions of records, of points. Then in those cases, you need to use kind of data shader, PyDeck, Bokeh, or Baek, or something like that to, let's say, or it's what, if you are familiar with Grafana, is what Grafana used to do, is to decide at what scale you are looking into the image, and then it provides kind of general overview at that scale. If you go closer or far away, then it will react in consequence, and then it doesn't need to collect all the data to do the job. It makes kind of on-site filtering, potentially even at the database level. Then that is the tools that we need to be familiar with. Then as a summary for machine learning and deep learning, depending on data type, data size, etc., I provide you that table, which try to help you when to get focused on one side, on one technique, on family of techniques, or on another one. Then when we deal with supervised learning, big critical issues me, myself, normally used to make, and then probably you as well. first of all, try to be very careful avoiding training and validation, for sure, unexpectedly, data, because then we are completely destroying either the learning process if you make the training and the validation, you mix them, or the assessment and the quality of the model if we make a mistake between training and test. Because in that particular case, we are measuring the quality over samples that were already seen, and then the model it should be familiar with, and then it is kind of biased, inducted by yourself. So if you create a model and you get let's say, imagine you are doing a regression, and you get a R square of 1, and it's not a trivial linear model, say something wrong is here, potentially 99.99%. And potentially because of either the duplication or mixing training and test or whatever stuff will be relevant. Or the same if you do classification and you get 100% of the separation of classes. Instead, if there are a naive problem, otherwise it should not be happening that kind of good luck. Then other good recommendation is be careful about the imbalanced classes. Keep in mind, machine learning and even deep learning, they are concerned with creating model just based on data. If we tell them in my data, in my Excel file or in my SQL table, that 80% of the items are class A and 20 are class B, when you want to do inference, the model will think, okay, what is the probability of class A? As a beginning, 0.8, because it's what I learned. So if the user asks me for my opinion of that sample is class A or B, I will say class A, because the amount of expected error is much lower. So we are biasing dramatically the model without being aware of, but then be careful. We need to train models with more or less balanced data set in a way to avoid that kind of things. While it doesn't mean that when you use it for production, you can be as much in balance as you want. Critical aspect is to visualize feature correlation and feature analysis. This is what I told you before in the data understanding and the data preprocessing. It has a name itself, which is exploratory data analysis, EDA. So it is important because if you don't feel comfortable with your data, if you don't really believe what your data is saying, humans are not very good in doing mathematics at high speed, but our eyes are very, very informative. So showing a plot with the data and the relationship between axes then help us to understand behavior very, very quickly. In an aggregate way, for sure, it's not detailed, but the general overview is fantastic. And then it helps us to protect us to make very big mistakes. Don't forget them. So recommendation in the data preparation is do EDA, please, as much as possible. And then don't say, okay, I need to produce, my paper requires a very complex and heavy model. Let me jump into the latest generative adversarial network with some multi-heads and then extraction layer condensated in. Okay, maybe you need to go there, but my recommendation is start with a very simple linear model or whatever, or chunked model. Try to understand what this data says, and then based on that, you need to say, okay, now I need to go forward, and then I need to do whatever. So I don't prevent you to do the highest technology. My suggestion is try to grow smoothly and take your time to understand your data. And then for sure, be careful when selecting metrics, which is a very also common mistake. When I review a paper, normally I found that kind of issues there. So I'm doing classification and I use accuracy. And then I show a spectacular accuracy, fantastic. Then how's about the imbalance, for instance? Then we need to be very, very careful and to be very aware of potential mistakes. Or if we are very conscious related to false negative importance, then I need to use recall to be careful about that, because it will consider that in the metrics itself, so they will cover that kind of situation. Then, yeah, so in regression, for instance, root mean square errors or mean absolute error, for depending on what you want to consider, or both if you want to. R-square, that kind of thing. So be aware of that the metrics you use tells something which is relevant for you in terms of assessing the model. Don't forget that. Then another critical aspect is to prevent overfitting, especially for deep learning, but also for machine learning as well. Then try to penalize the growth of the coefficients with regularization, for instance, either lasso, reach, or whatever. And if you are in classification or clustering, or even regression, because there are trees specializing in regression, like gradient boost, for instance, or random forest as well, then try to prune the limiting the depth or the minimum samples to be considered in one tree, in one leaf of the tree. Then this is important, otherwise you will get the model replicating and learning the exact data you have and not the general behavior you want to capture, right? And then the recommendation is to monitor not just the learning curves, the training curves, but also validation. It's very important because it will show you when overfitting starts to happen. And then it's going to say, okay, if go forward, I will learn the data itself and not the model, the physics or the behavior I want to. And then since a step, if in the case you have no data, in that case, that could be a thing to avoid. Otherwise, in any other case, please use cross-validation, because there are situations where a combination, because you say, okay, I will do a 20 or 75, 15, 10 percentage of training, validation, and test. And then I will do it randomly to prevent any kind of behavior. Yes, that's fine. It's good. But still, there are parts of the data you will not realize how it behaves. Those related to validation and to test. Right? So somehow there is kind of what if best cases are in the 75% you use for training, or wrong cases, then you can discard models or accept models which are not so good. So cross-validation will prevent you on that kind of situation. And indeed, the second advantage is that it will produce you either 5 or 10 models. You can stack them, and then you can get less variance in the outcome in the end. So it's a little bit more expensive, but in terms of computation effort, but normally it worth the effort. Okay, then other things in that particular case for unsupervised learning. So here data preprocessing is important in any case, but here is absolutely critical. Then don't forget here to scale features, because remember, here there is no ground truth. The only thing we have is distance between elements, between items. So if we have bias because of large variation against short variation, we will get confused. Either we have Mahalanobis distance or any other compensating that, or otherwise we will confuse the model immediately. So try to avoid. And then be careful with the high dimensionality, because here the distance is critical, and the course of dimensionality, what will take you is to consider for the samples you have in higher dimension, the distance is getting the same. Actually, it's kind of getting like all the samples get concentrated in a single point, more or less, is the idea of the course of dimensionality. So be aware of, try to make a dimension reduction for that. That will help you a lot in that particular cases. And then, of course, try to do robustness analysis and try to incorporate pre-existing knowledge in the field, because it helps you to understand if your behavior, your feeling about the number of clusters, the type of the behavior of each cluster, etc., makes sense or not. Right? Related to the example I showed you before, for the data, for the energy prediction, here you will see what I told you before related to how to prepare the pipeline. So the preparation of data, so the extraction, the loading, let's say, the preparation of data, the selection of features, training, and then when the models are built and validated, then inference, that will be the gain. So I show you some examples but probably there are the typical thing you have as well. So then let's say I try to create from a nano banana of Gemini kind of illustration for the thing. Okay, don't forget to try to avoid correlation. So the duplication need to be removed. Then don't forget to do it. But also don't forget to use tools to identify relevance of feature, because you can have previous knowledge that that feature is relevant, that other is much less, etc. But it's good to test based on your data and to check the alignment between your belief and what the model says. And don't forget here to penalize the regression of elastic net. And then based on that, finally, before jumping into the creating the models, try to analyze the relevance of the features. Although you are using let's say a easy model like linear model or whatever, try to start with all the features and try to remove and to check how many of them, depending on the relevance you got, depending on the relevance, how many of them can be removed and still producing a relevant model. How much variance you lose by removing the specific features, because then you can assess and measure the quality of the model by bias information criteria or archaic information criteria or any other, and to identify and to find for a good balance between all the things, right? So yeah, just coming back in an example, I don't want to, because of the time, I don't want to waste more time. Then I wanted to show you, if you see this, you see here one model, a linear model with penalty, with reach, producing, well, not bad model. You see, this is the reality axis and the predicted, then the variability is like this, and the error graph based on the samples is like this. So you can say, okay, it's not bad model. Especially if you see this, say, okay, it's inside the, let's say, the band of performance I expected, so why not? Then it's good. My suggestion is try to do other models and to check. This is a random forest, for instance. Say, okay, this is even better. You see, it improves by reducing the error by 50% more or less. You see the MAE is reduced by 50%. And then obviously the R squared grows. Then say, okay, good, not bad. Then I will discard the linear model and I will retain the random forest one. Why not? Then all my checks works like this. Then I go forward and then I found this model. Here is even better. The previous one was in 9 point whatever kilowatts per hour of error. This is a point for 6. So it improves 30% in the error, and it improves between 0.92 until 0.97. Say, wow, this is my model. Yes, if you see this, The answer is yes. If you see this, say A, be careful. This is bias. So the behavior is not, the heteroscedasticity is not well accurate, it's not consistent. So in that particular case, that model will be good for the very low values of energy, but not for the very high. And then not for all, for sure. Right? So be careful. Then you see here the advantage of stacking. In that particular case, this is the stack of those previous models, and you see how it outperforms all of them. But still, the good thing is that it doesn't make the mistake that the gradient boost made here, but it's more or less consistent through all the spectrum, let's say, which is something. Then these are the things that we need to check to assess our models and to be convinced and to understand what is going on there. Right? Okay. Then approaching the last part of the discussion, transfer learning. I suppose you are familiar with transfer. The idea here is, okay, I have no enough data to train a deep learning model from scratch. Then I need to, but fortunately, the thing I want to do can be related to that other problem, that other domain where there is already a public or private deep learning model already trained. Why not to transfer the domain knowledge? Why not to use that model to adjust to my case? This is the meaning of the transfer learning. It's fancy, isn't it? So then the idea here is, well, for sure, you need to use good hardware, graphical processing units, etc., but you don't use it for longer, like if you need to train from scratch a deep learning model. Indeed. So still, it's not out of the schema, but at least you reduce the effort. So things, well, the idea is how to do the job. The idea is, okay, let me, because in the deep learning model already trained, I'm using to adapt into my field. Normally, the deep part of the model, the initial part and the middle part of the model is related to the basic knowledge. So I wanted to frozen that, to keep that frozen, because this is what the part of the domain I want to preserve. And then I want to adapt the last part, normally the last layer of the models, trying to adjust and see what is possible to reach with that kind of models. Then this is the strategy I suggest you to do, is doing a fine-tune based on the very last part of the deep learning model you already got. Then you are able to, if you have the sources of the model, you can say, okay, let me load the weights, and then let me load the structure, and then let me relax and open for optimization the weights for the last layer. And then let's see how it adapts to my case. Then as I'm training a very short number of weights, then it should be easier to find a good match and with less samples, let's say, which is the critical point. Then this is the idea. I will show you an example. And the example is try to identify, let's say, the geometry in metallographic material. So imagine you got a microscope image, which is this one, showing different phases here, like ferrite, carbonites, etc. So different components. And then you want to analyze the image automatically and label the faces in one shot like a human people. But unfortunately, we don't have deep learning. This is an image domain, so deep learning should be applicable, but we don't have. But we thought that, okay, but what we need to do here? We need to make kind of segmentation of these regions and then to classify them into a category. This is what is expected, right? Well, why not to use that kind of approach where people train already models to do image analysis, image segmentation, that kind of things. Probably you remember the YOLO model. YOLO is a well-known model. Probably you saw it in many videos, etc., because it's used to identify people moving from cameras, for instance, in a scenario, and tracking the persons moving all around. They put a kind of box around the people. This is YOLO. YOLO is trained to do that kind of stuff. Actually, it's kind of, in that particular case, YOLO is identifying people or objects, let's say. In my case, it's not objects, are regions what need to be identified, but basically the concept is the same. So why not to use YOLO plus something to do the job? And then this is what we did as an example, and the outcome is out there. So for sure, we use, there is no free lunch again, so we need to have annotated images. So people who with a pen goes over here, mark this region, like this is one material, this is ferrite, this is martensite, this is whatever, right? Then, indeed, the system is able to do the job. It's not perfect, but still is not bad. So this is the idea for transfer. So the idea here is to do the raw input, the pre-processing. In that particular case, we need to adapt the image to the YOLO format to use it. And then, because we have only 36 annotated images, so keep in mind, we need the image, the micrography from the microscope, but also the human annotated image for using it as an input. So the input is the two things, the image and the regions annotated by humans. And then we do have a very limited number of samples. Then here cross-validation doesn't apply because of obvious reasons. And then, well, the performance, if you see the precision, say, wow, not bad. Yes, but actually the false negatives are relevant and the recall you see is much, much lower than that. So, well, with 36 images is what we should be expected. So there is no freelance again. But still, it's a technology that will help us to move forward. And then say, okay, makes sense to grow the amount of annotated images to increase the numbers and the values of the experiment. Then this is for the same application, for the metallographic segmentation, etc. The training loss, or the training error, and the validation error. I plot U for U. Well, in YOLO, there are different things because there is a segmentation from one side, and then there is a identification of regions, which is the box loss on the other side. Based on this, what you see is that only 10 iterations, 10 epochs make sense, because after that, overfitting starts to happen. You see, by 10 epochs, you will get the end of the story perfectly without no discussion. Then, last but not least, recurrent learning, reinforced learning, sorry, which is here the schema is that it's a completely different problem. Here we want to learn from experience in the very meaningful sense. The idea here is to learn through time. So it's not based, it's not grounded for solving or learning from static samples. For that is machine learning or deep learning. Here is the problem is when things evolve and things from one state to another depends on the previous state and depending on the decision made. Then this is when reinforced learning make full sense. For instance, imagine to predict stock market evolution based on decisions. Then the evolution will depend on the decision made before. Or when there are delayed gratification. So I make a decision now, but the effect will come very, very late. So several iterations late. Then to take that back is not easy from the classical deep learning techniques. Then this is where reinforced learning makes sense. So here there are some tics like be careful to this. Here the key point is to define one environment, and the idea is here to operate agents able to make actions based on a reward, moving in the environment you define. So the key point here is to be very clear in the definition of the environment itself and the reward themselves. And the action is more or less defined because it's what you want to do, changing from one status to another one. So this is basically fixed somehow, but not the case for the environment nor for the reward. And then just to show you a very short example, because we need to finish, just keep in mind that if you have one example of the reinforced learning is the way that a vacuum robot works. It uses reinforced learning to identify regions, etc., and to define the strategy to how to clean that things. But the problem is that the agent driving the game is very well trained. So imagine that we say to the agent, hey, I will reward you for cleaning dust. Then be sure that the agent will discover that if it cleans and it releases what it cleaned and clean again, since it will get reward, it will do that and it will not clean your house anymore. So this is a clear example that you need to be very careful on how the reward strategy works, because it's very easy to get it working wrongly according to your expectation. And then try to be very, as I written there, is try to be dense in terms of reward. So don't just to provide reward when it is well done, perfectly well done, because then there are few cases, and then the agent will be very hard to discover those situations, and then it will never progress normally. So it's better to say, okay, you did well, not perfectly, not 1, but you did 0.1. If you do that, and then here you get 0.2 or 0.25. So it's much in that way to try to promote behavior and then try to make the agent to evolve, because it's for it matter of time to learn, right? And then recommendations, don't start doing reinforced learning from scratch. Try to rely on already, as I told you, strategies provided that helps you to doing a very good job, and then try to test your agent and try to be the reinforced learning is very dependent on the seed, on the initial starting point. Try to get frozen it to, at least for the preparation, to be sure on how the evolution is going to happen and what's going on, right? And then try to try to identify what is already known and what is the advantage for the reinforcement. Otherwise, you can get confused, because that will be done much more easiest by using deep learning or whatever. Then another very last but important thing is try to follow the dynamic of the behavior of the agent, because here the metrics, which is a static thing, is important, but it's not so important like the evolution. So here let's say the tracking of the agent is very, very important. So don't forget it, and then try to track the evolution of the agents themselves. I place you an example and some papers here if you are interested in reinforced learning, based on basically market analysis of the strategies for investment. And well, that's all from my side, trying to show you a little bit the panoramics of the machine learning, deep learning, transfer learning, etc. If you have questions, specific, generic, whatever, feel free to place them into the chat, and I will try to handle them. Sorry for being 8 minutes longer than expected. Not sure if there are questions. Thank you for attending the presentation, for the patient seeing moving slides. Then the material will be available for you later, for sure. Feel free to either write questions or just unmute and tell the question as well. I can handle For sure, Spanish, French, and English questions, I think I can handle that. Thank you to you for attending it. I think I will stop the recording.